Hi everyone, let us start the sixth part of Module 5, which is simple harmonic motion. This is not a new topic to you because you have already studied it in your higher secondary classes, like what are the terms and equations related to simple harmonic motion. We'll be studying the same thing, and along with that, there will be some more problems. So let's see. So first one is mechanical vibration. Based on the direction of motion, the mechanical vibrations are classified as longitudinal, transverse, and torsional vibrations. So let us see the figure, then it will be more clear. First one is longitudinal vibration. We consider a spindle. It is attached to one end and at the other end there is a weight. Now assume that this weight is pulled downwards and then released. What happens? It will be vibrating in the up and down direction, isn't it? Which means it will be vibrating in the longitudinal direction. So this type of motion is called as longitudinal vibration. We can spot out many examples for it, but one example which we will be discussing in this chapter later is spring mass model. So this is a spring mass model in which there is a spring attached to it, there will be a mass. Now assume that this mass is pulled downwards. Then what happens? Then it will be translating in this up and down direction, isn't it? So that's an example for our longitudinal vibration. Now the second one is transverse vibration. So from the figure itself, we'll be getting an idea. And there is a spindle, there is a weight. If it is pulled to one side and then released, what happens? It will be vibrating in the transverse direction. It will be vibrating in the transverse direction. So that type of motion is called as transverse vibration. Now examples for that, we have already studied an example which is simple pendulum, which means it will be translating from one end to the other end. Now another example which can be spotted out in our daily life is a swing, which means what we normally call unyal in our language. So consider that swing itself. What we normally do is we will be pushing it from one side, then it will be vibrating in the transverse motion. So this swing itself can be made as an example for many of the terms. We will see it. So that is transverse vibration. Next is torsional vibration. What happens in torsional vibration? Again, there is a spindle and weight. Now assume that this weight is twisted to one side. It is just twisted to one side and then released. What happens? It will be moving in a twisting manner, or it will be having torsion, like it will be moving to and fro. So by seeing an example, it will be more clear. Again, assume the same swing itself. Now normally in swings we'll be pushing it from one side and then it will go to the other side and come back. But in some cases, just for fun, we'll be twisting it to one side. The same swing, we'll be twisting it one side and then released. What happens? It will be twisting to the other side, or it will be rotating to the other side, and after sometimes it will be rotating back, and again it will be rotating to the other side, and it will be rotating to the next side. So that's an example for torsional vibration. So these were the classifications of mechanical vibration based on the direction of motion, that is longitudinal direction, transverse direction, and torsional vibration. Now let us see two more classifications of vibrations or different types of vibrations. It is free vibration. The first one is free vibration. Next one is forced vibration. So let us see what is this free vibration is. So from the name itself, you will be getting an idea. Free vibration means initially we will be giving a vibration to the body, and after that it will be moving in its periodic manner. And finally it will be coming to a stop. It is stopping because there is a loss of energy from the system and hence it stops. So let us see what is written over here. A mechanical element is said to have a free vibration if the periodic motion continues after the course of the original disturbance is removed. The free vibration of mechanical system will eventually cease because of loss of energy from the system. So the same thing. Initially we will be giving a vibration, and after that it moves in periodic manner, and finally it will be stopping due to loss of energy. What is the example for it? Again, the same swing itself. Assume that initially only we'll be giving a push to the swing. Then it starts vibrating in the transverse manner and finally it stops, isn't it? That stopping is because it is due to the loss of energy from the system. Now, forced vibration. So, what will be forced vibration? Again, initially we will be giving a force to the system, and after that when it is stopping we will be again giving force to the system, and hence it will be vibrating, and after that again when it slows down we will be again giving it a force, and again it starts vibrating. So that is at regular intervals we are giving the forces to the system, and hence it is vibrating. So it is forced vibration. So it is a system is said to undergo forced vibration when a periodic disturbing force acts on the system. In forced vibration, the system will vibrate at the frequency of the existing force regardless of the initial conditions of the system. So what is the second sentence? Again, we can assume the same swing itself. What happens in a swing? Initially, we will be giving a push to the swing, and after that, it slows down, and then again we are giving a push to the swing. Again, it start vibrating. So at each time, we can see that it does not depend upon the initial force, but depends upon the force which we are applying the next time. That is, when it slows down, we are again giving it a force, and it will be vibrating at the force of the current system, at the force given right now. So that is the second sentence. It will vibrate at the frequency of the existing force regardless of the initial conditions of the system. So that is free vibration and forced vibration. Now next is period of vibration. So all these terms you have studied already. What is this period of vibration? It is the time interval required, or it is the time interval after which the motion is repeated itself. Or in other way, we can say that it is the time required for one complete oscillation. So if you are assuming this simple pendulum itself, this is a simple pendulum. Let it start from A point, then it goes to O, and then it goes to B, and after that from B to O, and from O to A. So the time required for this complete oscillation means from A to B and from B to A, then only it completes an oscillation. So the time required for this complete oscillation is called period of vibration, or in other way we can say that it is the time interval after which the motion is repeated itself. That is, from A to B it goes, and from B to A it comes, and after that again it repeats. So both definitions are okay. Next term is frequency. So what is frequency? The number of cycles per unit time is called frequency. Per unit time means it may be either in seconds or in minutes, which means number of cycles it has completed per seconds, or number of cycles it has completed per minute. That is frequency. Now we have already seen this free vibration. The frequency of free vibration is called natural frequency. So just a term, natural frequency means it is the frequency of free vibration. Next term is damping. What is this damping? So we know that a system is vibrating, and after that and if any resistance is given to the vibration of this system, then it is called as damping. So any resistance to the motion of a system is called damping, and we can see that in the case of free vibration, after some time it will be stopping. So it is due to this damping force which it comes to a stop. So what happens is that due to this damping force, the amplitude of vibration decreases, and finally the system comes to a stop. Now what is this amplitude of vibration? It is the distance between the mean position and extreme position of a vibrating body. We can take the same example itself. Mean position means this is simple pendulum. So this is the mean position, that is center position or equilibrium position. We can say it in many ways. This is the mean position or equilibrium position or center position, and these are the extreme positions A and B. So it is the distance between this mean position and the extreme position. So from O point to A point or from O point to B point, the distance is termed as amplitude of vibration. Now there is one more term which is degree of freedom, in bracket DOF. So from the name itself, you will be getting freedom, degrees of freedom in which all directions which we can move. That is degree of freedom. So if you are considering a body or a system, normally it will be having 6 degrees of freedom in a space. If it is in a space, which means 6 degrees of freedom means it can move in x direction, y direction, z direction, or it can rotate in x direction, y direction, and z direction. So normally a body in space will be having 6 degrees of freedom. Now if we are considering a single degree of freedom system, here in this module we will be discussing about single degree of freedom system only. So first case is what we saw in the early case itself, spring mass model. So there is a spring, there is a mass attached to it, it will be vibrating in up and down direction only. So that is an example for single degree of freedom. Similarly, simple pendulum, this example. In simple pendulum also, it will be vibrating from A to B and from B to A, which means it is having only 1 degree of freedom. And that is not based upon X, Y or Z direction, but it is based on this theta value. Based on this theta only, it will be having the degree of freedom. So these two examples we will be studying in detail in this module. Now let us see what is this simple harmonic motion. Simple harmonic motion is a periodic motion. Now what is periodic motion? Any motion which repeats after regular interval of time is called periodic motion. So we can say simple harmonic motion is a straight line motion. So let us see how it is a straight line motion. Before that, all the periodic motions will not be simple harmonic motion. There are two conditions which should be satisfied if it is to be a simple harmonic motion. Let us see what are the two conditions. First one is the acceleration of the body performing periodic motion should be proportional to the distance of the body from the mean position. The second one is the acceleration of the body should always be directed towards the mean position. So consider a simple pendulum. From this itself we can say. So we can see that here this is the extreme position as we told earlier. This is the mean position or equilibrium position, and this is the extreme position at the other side. So the first condition is from the mean position, if you are considering any other point, let it be some points over here or here, or let it be the extreme position. So we can say that as it is moving from the mean position, that is as the distance increases, the acceleration will also increase. Or when the acceleration, when the distance decreases, the acceleration also decreases, which means we can say that this acceleration is proportional to the distance from the mean position, isn't it? So that's the first case. The acceleration of the body performing periodic motion should be proportional to the distance of the body from the mean position. If the acceleration is a and the distance is x, then we can say that a is proportional to x. Now the second condition is the acceleration of the body should always be directed towards the mean position. So if you're considering again this position, the acceleration of this body should be towards the mean position, which is shown by this arrow mark. Let it be another point somewhere over here. Then also it should be directed towards the mean position. So these are the two conditions which should be satisfied for a periodic motion to be simple harmonic motion. Now let us see some equations for simple harmonic motion. Before that, consider this figure. Consider a particle is moving along a circle. Consider a particle is moving along a circle which is having a radius r and it is having an angular velocity omega radians per second. So it is moving from A to C, then B, then again from B to D, and again to A. O is the center portion. R is the radius, omega is the angular velocity. Now consider at any particular instant t, let P be the position of the particle. So as it is moving from this position to this position, at a particular instant, let P be the position of the particle. Now what we are doing is we are projecting this P to the horizontal line AB. So this P is projected downwards to the line AB. Let M be the projection. So at this particular point P, M is the projection on the horizontal line. Now let this particle is moving from this position to another position. Let this be the position. So we can say that at that particular position, let us see, at this particular position, what will be the projection? This will be the projection. Now again, if this particle is moving along this circle at this particular position, this O will be the projection on the horizontal line. Now again, if it is moving on this circle, this is the point P, it is moving in, now it is at this point. So this when it is projected downwards, this will be the position. Or if it is again moving, we can say that this is the horizontal projection. So at each time we can see that as it is moving from this A point to C and from C to B, we can see that in the horizontal direction it is moving from, this M is moving from A to B in a straight line, isn't it? As the particle is moving along a straight circular path, this M is moving along a straight line motion. So that is what we call symbol harmonic motion as a straight line motion. This is the straight line motion. So we can say it as a symbol harmonic motion. So similar is the case when it moves from B to A as well as from C to D also. So all those things are said over here. You can just go through it. Okay, now let us see what all are the equations related to symbol harmonic motion. There are two cases. First case is when it is measured from the mean position, and the second case is when it is measured from the extreme position. So let us see the first case. In both the cases, the equations are almost similar. Just a difference is there in the first equation. Okay, let us see. The first one is the distance x is given by x equal to r sine omega t into 180 by pi, where x is the distance, r is the amplitude, omega is the angular velocity, and small t is the time at a particular instant. So why this 180 by pi? This is because normally this will be in terms of radians. So in order to convert this radians into degrees, we are multiplying it by 180 by pi, because we know pi radian equal to 180 degree. So 1 radian equal to 180 by pi. So normally we will be saying everything in terms of degrees, isn't it? Sine 30, sine 45 degree, sine 60 degree. So in order to convert this radians into degrees, we are multiplying it by 180 by pi. So if it is from the mean position, x equal to r sine omega t into 180 by pi. And if it is from the extreme position, it is x dash equal to r cos omega t into 180 by pi. Instead of sine, it will be cos. Here, you can write it as either x or x dash. In the problems, most probably we will be writing it as x itself. It doesn't matter. The only thing to be remembered is if it is from the mean position, it is in terms of sine. And if it is from the extreme position, it is in terms of cos. So x equal to r sine omega t into 180 by pi for mean position, and if it is for extreme position, it is x dash equal to r cos omega t into 180 by pi. Now the remaining equations will be the same thing, which means velocity equal to, this is the differential of this distance, which means v equal to dx by dt, or we can write it as v equal to omega into root of r square minus x square, where omega is the angular velocity, r is the amplitude, x is the distance. Here also the equation is same for extreme position also. And the next equation is maximum velocity Vmax is given by omega into r. Here also it is same. Acceleration is given by omega square x. So here also it is same. All the equations are same in for both mean position and extreme position. Only the first equation changes. So the maximum acceleration is given by omega square into r. What does that mean? At a particular time, it is x. So it is omega square x is the acceleration. Now for acceleration to be maximum, this x value should be maximum. And when it is maximum, x means it is the distance from the mean position to while going to the extreme position, that is the distance x. And it is maximum when it is moving from mean position to the extreme position. And that distance is the amplitude r. So that's why Emax equal to omega square into r. And we also have frequency is given by frequency equal to 1 by time period. Frequency is f, t is the time period. Capital T is the time period. Now don't get confused between this capital T and small t. This small t means it is the time at a particular instant. and capital T is the time period. So time period means, it is the time required for one complete oscillation, and the small t means at a particular instant, the time. Now we have a relation between angular velocity and frequency. It is angular velocity is equal to 2 pi into f, or we can write it as f equal to omega divided by 2 pi, or we can write it other way as t is equal to 2 pi by omega. I think this equation you have studied, or it is better to remember this equation: t is equal to 2 pi by omega, or f equal to omega by 2 pi. So in all these cases, apart from the first equation, the remaining equations are same, but don't think that in both the cases the answers will be same, because it depends upon this x value. As the x value is different in both cases, the final answers will also be different. Now let us see the problems. First problem is, a point moves with amplitude of 1 meter and time period of 2 seconds. Find the velocity and acceleration after t equal to 2 by 5 seconds when time is measured from mean position and extreme position. So here there are two cases, mean position and extreme position. Initially, what all things are given? Amplitude r is 1 meter. Time period capital T is 2 seconds. Now velocity and acceleration to be determined at a particular time t, small t equal to 2 by 5 seconds. So let us see the first case, mean position. If it is mean position, what was the equation? X equal to, in terms of sine. So x equal to r sine omega t into 180 by pi. What all things are given? R is given, which is 1 meter. Small t is given, which is 2 by 5 seconds. What about this omega? Omega is not given directly, but instead time period is given. So what is the relation between omega and time period? We have omega is equal to 2 pi by t. So substitute over here, you will be getting omega equal to pi radians per second. So substituting all these things, you will be getting x as 0.95 meter. Now what is to be calculated? Velocity and acceleration. Velocity is given by v equal to omega into root of r square minus x square. So omega is given to you, r is given to you, x value you already got it from here. Just substitute over here and you will be getting velocity as 0.97 meter per second. Now to find acceleration, we have the equation a equal to omega square into x. So just substitute over here and you will be getting 9.37 meter per second square. So you will be having a doubt whether to use omega square x or omega square r. So if it is the maximum acceleration, it is omega square r. But here it is told us to find the velocity and acceleration after t equal to 2 by 5 seconds. That is at a particular time, it is given by a equal to omega square x. In case when it is asked to calculate the maximum acceleration, then only use amplitude value omega square r. Similarly, if it is extreme position, what is the equation for x? X equal to r cos omega t into 180 by pi. It is cos term. So the terms will be same itself. Values will be same. Omega is equal to pi radians itself. R is equal to 1. T is equal to 2 by 5. Just substitute over here. You will be getting 0.309 meter x value. Don't forget this value 180 by pi, because if you're forgetting it, the remaining values also will be wrong. So don't forget about this 180 by pi, and don't get confused between this sine and cos. From the mean portion it is sine, and from the extreme portion it is cos. Similarly, velocity value is v equal to omega into root of r square minus x square. You will be getting 2.98 meter per second, and acceleration equal to omega square x, from where you will be getting 3.05 meter per second. Even though the equations for velocity and acceleration is same, you can see that the values are different. It is different because the x value is different. As the x value is different, the remaining values also will be different. Okay, next problem. Find the velocity and acceleration after 0.3 seconds from the extreme position of body moving with simple harmonic motion with an amplitude 0.8 meter and period of oscillation 1.6 seconds. It is just similar to the previous problem itself. What all things are given? Amplitude is 0.8 meter, period of oscillation capital T is 1.6 seconds. Now time at a particular instant is 0.3 seconds, that is small t equal to 0.3 seconds. As it is from the extreme position, what is the equation? X equal to r cos omega t into 180 by pi. What all things are given? Amplitude is 0.8, small t is 0.3. What about omega? Omega is not given directly, but instead period of oscillation is given. So omega is equal to 2 pi by t. So you will be getting omega equal to 3.925 radians per second. Just substitute over here and you will be getting x value. Velocity is omega into root of r square minus x square. All these values are given. So you will be getting velocity equal to 2.9 meter per second. Acceleration is omega square x. Again you will be getting 4.71 meter per second square. So there is nothing new in this second question. It is just similar to the first problem itself. Now third question. A body is moving with simple harmonic motion and has velocities of 8 meter per second and 3 meter per second at a distance of 1.5 meter and 2.5 meter respectively from the center. Find the amplitude and time period. So this is from the center. Center means it is the mean position. From the mean position it is given. So what all things are given? The velocity is 8 meter per second when it is at a distance of 1.5 meter. That is, there are two cases. Let v1 be 8 meter per second when the distance x1 is 1.5 meter. Second case, when the velocity is 3 meter per second, the distance is 2.5 meter, which means v2 equal to 3 meter per second and x2 equal to 2.5 meter. Now what is the relation between v and x? We have v equal to omega into root of r square minus x square. So there are two cases. You will be getting two equations. Solving those two equations, you will be getting the final values. So let us see. Let v1 equal to omega into root of r square minus x1 square. Here, as it is moving, only the velocities and distance are changing. The amplitude won't change because it is the maximum value, and omega, angular velocity, also won't change. So let us see. First case, when it is v1 equal to 8 meter per second and x1 equal to 1.5 meter. Just substitute over here. v1 equal to 8, omega is unknown, r is unknown, x1 is 1.5. So that is equation. Now for equation 2, we have v2 equal to 3 meter per second and x2 equal to 2.5. Just substitute over here. That is equation 2. Now equation 1 by equation 2, you will be getting like this. So solving these two equations, finally you will be getting the r value, which is amplitude, which is 2.63 meter. Substitute r in either equation 1 or equation 2, and finally you will be getting the angular velocity omega, which is 3.71 radians per second. And you have been also asked to find the time period. So relation between omega and time period is t is equal to 2 pi by omega. Just substitute over here and you will be getting time period as 1.69 seconds. Okay, next problem. A body performing simple harmonic motion has a velocity of 12 meter per second when displacement is 50 millimeter and 3 meter per second when displacement is 100 millimeter. The displacement being measured from the mean position. Calculate the frequency and amplitude. What is the acceleration when the displacement is 75 millimeter? So this problem is also similar to the third problem what we have seen, but here it is in terms of millimeter. So first thing what you have to do is convert this millimeter into meter, which means the velocity is 12 meter per second, which means v1 equal to 12 meter per second. Corresponding displacement is 50 millimeter. So x1 is 50 millimeter, it is 0.05 meter. Now when velocity v2 is 3 meter per second, displacement is 100 millimeter, or it is 0.1 meter. Now we will be doing it by the same method, just like what we have seen in problem number 3. So not discussing all those things. So this is equation 1 and equation 2. Solving equation 1 and 2, you will be getting the amplitude as 0.102 meter and omega value is 134.97 radians per second. What all things are to be calculated? Amplitude and frequency. Amplitude we have already calculated. Frequency, to calculate frequency, we have omega equal to 2 pi f, or f equal to omega divided by 2 pi. And there is one more part which is to be seen. What is the acceleration when the displacement is 75 millimeter? So we will see it. So we have omega equal to 2 pi f. So we got the frequency as 21.49 hertz. Now acceleration and displacement, what is the relation? A equal to omega square x. We already got the value of omega x value. It is given in the question as 75 millimeter. So convert into meters, which is 0.075 meter. Next problem. A body is moving with simple harmonic motion and has an amplitude of 4.5 meter when period is 3.5 seconds. Find the time required by the body in passing between the 2 points which are at a distance of 3.5 meter and 1.5 meter from the center and are on the same side. Okay, so this seems to be a different question. Initially, what all things are given? Amplitude r equal to 4.5 meter. Period capital T is equal to 3.5 seconds. Now the next thing is find the time required by the body in passing between the 2 points which are at a distance of 3.5 meter and 1.5 meter from the center. So it is calculated from the center and are on the same side. So it is better to draw a figure. So consider a line AB. AB, this is the center point O. Now, from this center point, it is measured. It is at a distance of 3.5 meter and 1.5 meter from the center. So let this point be C and D, where this OC distance is 1.5 meter, which is x1 is 1.5 meter, and this distance is 3.5 meter. Why is it marked on the same side? Because it is said here, and it is on the same side. So same side of this center point. So it moves from O to A. In between there are 2 points C and D. It is having a distance of 1.5 meter and 3.5 meter. So from O to C, as it is x1, let t1 be the time required to reach x1, and from O to D the distance is x2, and the time required to reach x2 let it be represented by t2. Now we have the equation for that. From the center position, the distance is given by x equal to r sine omega t into 180 by pi. So that's the general equation. Now there are two cases, x1 and x2. So let us consider each case. So x1 equal to r sine omega t1 into 180 by pi. What is given? X1 is given 1.5 meter equal to r value. Amplitude is given 4.5 into sine t1 is unknown. Let it be t1 itself. What about omega? Omega value is not given, but time period is given, which is 3.5 seconds. So omega time period relation, omega equal to 2 pi by t. So you will be getting omega equal to 1.79 radians per second. So substituting over here, you will be getting like this: 1.79 into t1 into 180 by pi, or solving this 1.79 into 180 by pi, you will be getting 102.61 t1. So it is 0.33 equal to sine 102.61 t1. Here the only unknown is t1. How to find t1? Just take sine inverse 0.33. So you will be getting like this, and finally t1 is 0.189 seconds, which means from the center position to the distance x1 time, you got it as 0.189 seconds. Similarly, second case also, it is x2 equal to 3.5 meter. The remaining things are just same thing, and finally you will be getting t2 as 0.59 seconds. That is from O to D, or this, for covering this x2 distance, the time required is 0.59 seconds. What you have been asked is the time required by the body in passing between the 2 points, which means from C to D, what is the time? From O to C it is t1, which is 0.189 seconds. From O to D it is 0.49 seconds. So from C to D, the time required is t2 minus t1, which is 0.49 minus 0.189, which is equal to 0.301 second. Okay, let us see the last problem. In a mechanism, a crosshead moves in a straight line in simple harmonic motion at distances of 125 millimeter and 200 millimeter from its mean position. It has velocity of 6 meter per second and 3 meter per second respectively. Find amplitude, maximum velocity, maximum acceleration, and period of vibration. If the crosshead weighs 0.3 Newton, calculate the maximum force on it in the direction of motion. Okay, this problem is also similar to what we have seen in the early cases, like distance is given, velocity is given. Two cases will be there. So what is the first thing to do? We will be converting this millimeter in terms of meter. So the distance is, first case is x1, which is 125 millimeter, so it is 0.125 meter, and the corresponding velocity is 6 meter per second, which is v1. Second case, x2 equal to 200 millimeter, so convert it. So it is 0.2 meter, and velocity v2 is 3 meter per second. Now we have x1 v1, x2 v2. What is the relation between these two? V is equal to omega into root of r square minus x square. As there are two cases, just like what we have done in the previous two problems, the same thing is applied over here also. So equation 1, equation 2, solving those two equations, you will be getting the amplitude, which is 0.22 meter, and substituting this amplitude in either one of the equations, you will be getting omega value also. So up to this we have seen in the previous problems how to calculate r and omega. So what is being asked? To find the amplitude, we have already calculated. Now, what about maximum velocity, maximum acceleration? What is the relation between maximum velocity and omega value? We have Vmax equal to R into omega. So R is amplitude, you already got omega value, you already got it as 33.14. So just substitute over here, you will be getting maximum velocity, which is 7.29 meter per second. What is the maximum acceleration? It is R omega square. So just substitute over here and you will be getting 241.63 meter per second square. And period of vibration. So as we have omega value, period of vibration will be t equal to 2 pi by omega, which is 0.19 seconds. And there is one more thing which we haven't seen earlier. If the crosshead weighs zero point 0.3 Newton, calculate the maximum force on it in the direction of motion. So there is a crosshead, it is moving in the direction of motion. What is the force required? So we have studied this relation in our previous classes, like force and direction of motion, kinetics. What is the relation? By Newton's second law, force equal to mass into acceleration, F equal to ma. So maximum force is m into a. What is mass? Instead of mass, weight is given 0.3 Newton. So mass is W by G, which is 0.3 divided by 9.81 into acceleration. As it is the maximum force, we will be having the maximum acceleration. So maximum acceleration is 241.63. Just substitute over here and you will be getting maximum force, which is 7.39 Newton. So that's all about simple harmonic motion. In this topic, initially we studied some terms related to simple harmonic motion. Those terms you have already studied in your +1 classes. Then you have seen equations and problems. While doing the problems also, you can see that if you know the equations, then it's just substitution only. No complications further in the problem. So this is a very simple topic and you can expect similar questions for your university exams also. So that's all for today. Thank you.